So we have already completed Unit 1, Unit 2, Unit 3, Unit 4, right? And today we shall start the Unit 5. Unit 5 is nothing but is soil reinforcement, right? See, you have been studying about the design of a structure 2, or that is also called a design of concrete structure, or reinforced cement concrete RCC, right? In 6 semesters also you have been studying. So what you have been studying there, that you are going to use the concrete along with the reinforcement. Reinforcement is nothing but the steel rod you are using, right? I would like to tell you that the concrete fails in compression, steel fails in tension, and soil fails in shear. That means what? We always used to talk about the shear strength of the soil. In whole soil mechanics, whenever we studied, the shear strength is very important, because based on the shear strength only you are going to calculate the bearing capacity of soil. But Unit 5 says that we have to talk about the soil reinforcement. Reinforced cement concrete, you are using the reinforcement rod along with the concrete. Here we are going to use the reinforcement, which may be rods, which may be different things. Bamboo also you can use, right, along with the soil, right? So in case of soil reinforcement, how we can define the soil reinforcement or reinforced soil? Reinforced earth consists of a compacted soil mass within which reinforcing elements or membranes, usually in the form of horizontal strip of metals, are embedded. Embedded means incorporated along with the soil. You see that we have already studied the compaction chapter, how we are compacting the soil for the earth dam, for the embankment, for road constructions, right? So whenever you are going to spread one layer of soil, then they are using the rollers for its compaction, right? Again you are putting another layers, and again you are going for the you are going for the rolling in road construction. So definitely we find the maximum dry density, optimum water content, right? And at that maximum dry density or optimum water content, you are compacting the soil in different layers, right? While you are going to construct the embankment or the earth dam or roads. Here, reinforced soil can also be used for the construction of embankment, earth dams, right? Retaining wall, or for many purposes. We shall see later on. See, reinforcing elements, whenever we talk about the reinforcing elements, in case of design of a structure 2, we have been talking always about the steel rod, right? But here, in case of soil reinforcement, we have to talk about the many reinforcing elements, that is the galvanized steels, stainless steel or aluminum alloys, rods of metals, wire grids, fiberglass strips, bamboos or geotextile. See, in the compaction chapter, what we have been doing, we are putting the soil, one layer of soil, then compacting. Again, we are putting the next layers, we are compacting. Again, third layers, compacting using the rollers, right? In case of soil reinforcement, how we have to proceed? What we have to do? What we can do? Just like compactions, we shall put one layer of soil. Above that, you have to spread, you have to lay down the reinforcing materials, which may be galvanized steels, maybe rods of the metals, maybe wire grids, right? I'll show you some figure later on in the next slides. And then again we shall put the another layer of soil, compact it. Again you put the reinforcement, and then next layer of soil, compact it. Likewise, we have to go for the soil reinforcement. So what is going to happen? The soil can take the compressive load. But once you are going to incorporate the reinforcing elements, what is going to happen? The soil will be able to take the tensile force. That benefit is there. So for that only, we are going for the soil reinforcement. You see, the essential feature of the reinforced earth is that friction developed between the compacted layers of the earth and the reinforcing elements. As I told you, that whenever you are going to construct the embankment, what you are going to do? You are going to put one layer of soil first, right? You are definitely maintaining the OMC and MDD, compacting by the rollers. So once you are going to complete the one layer, above that layer, you put the reinforcement, right? After putting the reinforcement, you put the another layer of soil, and then you compact that soil using the rollers. So once the second layer is compacted, then you put the reinforcement, and again third layer of soil you can put and go for the compaction using the rollers. So what is going to happen? The friction is going to be developed in between the interface of the soil and the reinforcement, right? If both the materials, reinforcing materials and the soil, both are going to be compacted, both will have a good grip along with each others, and they will take the more load. Even in case of foundation also, shallow foundation, we can use the soil reinforcement. So bearing capacity of soil will definitely it is going to improve, right? The soil transfer the forces to the reinforcement by means of friction. By means of friction, the reinforcing elements and the soil both will have a grip, will have a good grip, right? And the frictions are going to be developed there. So definitely the tensile force is also going to be developed. Tension will also be taken care of by the soil reinforcement. I would like to tell you that the soil reinforcement procedures was first developed by Henry Vidal, who belonged to France, right? What he did, he constructed a major retaining wall in France in 1968. We shall see some figure. See, whenever you are going for the soil reinforcement, three things are there. One, definitely soil is there. What will be the another things? Reinforcing elements will be there. And third will be the facing unit. When you are going to construct the retaining wall, right? The face of the retaining wall should be make good looking. It should look better, right? You can see here the components of reinforced soil and fill material is also there. The reinforcing strips are also there. This is the height of the reinforced earth. Second is the reinforcing strip, and the third is the facing if necessary. See, facing is you can see the facing unit. Facing is provided only for the beautification, only for giving the architectural view. Facing unit is not going to take the load of the structure, right? It is not going to take the load. The load is going to be taken only by the reinforcing element and this wire, right? We shall go to the next. We shall see some figures here. Different shapes of facing units are used for the beautification purpose. You can see a square facing panel, hexagonal facing panel, flexible facing panel. You see here also these facing blocks are kept just in front of the soil reinforcement. So you see that once facing unit is completed, then after that, behind that, we can go for the soil reinforcement, for the construction of embankment, for the construction of retaining wall, right? So you see the facing unit is constructed only for the beautification, only for the architectural view. It is not going to take any load, right? We shall see some more figures here. Facing units. how the facing unit looks. This also the facing panels. It is given in front of the embankment or retaining wall. See, once the facing unit is also shown here, and you can see the swell reinforcement. One facing unit is going to collapse, for example. In that case, you can see how the reinforcement along the swell has been compacted in a embankment, right? You can see some figures here also. As I told you in the beginning, put the first layer of swell, then reinforcement. Reinforcement may be these steel rods, maybe bamboo, maybe geosynthetic materials, right? Many more, which I told you in the first slides. So you can see how the reinforcement, here steel reinforcement had been used, and then it had been compacted. Again, another layers will be placed over that. So these are the some figures for the soil reinforcement. Now we shall go for the topic geotechnical properties of reinforced soil. This is also a part of your syllabus. So whenever we talk about the geotechnical properties of reinforced soil, we shall go for the both type of soil, the cohesionless soil or cohesive soil. When you are going to use the reinforcing element along with the cohesionless fill material, what should be the properties of the materials, right? If you are going to use the cohesive soil along with the reinforcing element, what should be the properties of the soil, right? Cohesive soil. So that is called as geotechnical properties of reinforced soil. So in case of cohesionless fill means we are going to use the you are going to use the cohesionless soil as a filling material. Cohesionless fill, the frictional fill, granular backfill is defined as good quality, well graded, non-corrosive material usually possessing a good angle of internal friction. What does it mean? If you are going to use the cohesionless soil, as you know that the cohesionless soils may be crushed rock, river sand or gravels, definitely it will have a more angle of shearing resistance. So it will have a more grip along with the reinforcing materials, right? So more grip will be there, more friction will be there, more angle of internal friction will be there along with the soil, more grip will be there. So that means it can take the more load, more tensile loads can be taken by the soil, reinforced soil. That benefit is there. So we shall see some material property, uh, how we have to select the cohesionless soil for the filling purpose. So first we have to check the density. See, reinforced soil structures are the gravity structures. We have also talked about retaining wall. Gravity structure, in other words, it can also work as a retaining wall. We can also use as a embankment, earth dam. Nowadays, at most of the places, it is used in the construction. The density of parent material has a direct effect upon the internal and external stability. Parent material means what type of cohesionless soil you are going to use, whether you are going to use the crushed rock, river sand or gravels. All materials depending upon the density of the materials, right? Here we are talking about the particle density, specific gravity. So depending upon the specific gravity, the structures will be better. Structure will be good, right? So density also play a role in the cohesionless fill. The next is the grading. As you know, and we have also studied earlier that the well-graded soil is always good compared to the poorly graded soil. A well-graded compacted soil provides the most advantageous condition to optimize the soil reinforcement property. Whenever you are going to use the well-graded soil along with the reinforcing materials, as I told you, reinforcing materials may be the steel rods, maybe steel plates, maybe bamboo, maybe geosynthetic materials, maybe galvanized iron sheets, right? Many more. So if the cohesionless wire is well graded, in that case more grip will be there and it will be more beneficial. It will give them more strength. Poorly graded are undesirable and may lead to problems of stability. Problems of stability means your embankment may collapse. Examples of grading suitable as a friction field. You can see this table. Grading limitation of friction fields. Normally we have to use the cohesionless materials which should pass through these different shapes, right? In different proportions. You can see right hand side. So these proportions we should maintain for the well graded cohesionless wire. Uniformity coefficient of uniformity. Uniformity coefficient is nothing but the ratio of the D60 by D10, ratio of the 60% of the sample of the effective size to the effective size, right? The maximum size of 60% of the sample to the effective size. It is a ratio. Effective size means D10. The particle passing through 10 micron size. The effective size is the maximum particle size of the smallest 10% of the sample. C we can calculate coefficient of uniformity. D diameter of the particle passing 60%, diameter of the particle passing 10%. Diameter means size of the particle. So the coefficient of uniformity for the cohesionless wire which you are going to use as a soil reinforcement should be greater than equal to 5. Then it will have a more or a good strength, we can say. You can see the next thing, pH values, chloride iron content, SO3 sulfur trioxide content, resistivity, and redox potential, oxidation reduction potential. See, these are the chemical parameters. So, what I am trying to say here, whenever you are going to use the cohesionless soil, you have to also test these chemical properties. pH values, chloride ion contents, sulfur trioxide also you have to test. You have to also test the electrical resistivity in ohms and oxidation potential, oxidation reduction potential also you have to test. These are the chemical properties which have also been tested for the cohesionless soil before its use for a soil reinforcement. These soil field properties are associated with the durability of the reinforcing materials. So if you are going to manage, if you are going to, we shall see the table. If you are going to have, you can see the table here. Aluminium Ly, copper. That means what? Suppose you are going to use this reinforcing material. Aluminium Ly, copper, hot dip, galvanized steel, stainless steel, fiber 10, polythene, geogrid. In that case, what should be the values of pH for the cohesionless soil? You can see for aluminium Ly, minimum pH value is 6, maximum is 8. For copper, 5 and maximum is 9. Similarly, maximum chloride content in chloride and content in percentage for the cohesionless soil should be 0.05%, 0.05% for aluminium Ly. For copper 0.05%. Similarly, maximum total sulfur trioxide in cohesionless soil. What should the values of maximum sulfur trioxide values? 0.5, 0.5, 0.1, 0.1 for different reinforcing elements. Similarly, minimum resistivity values ohm cm, in ohm cm 3000, 2000, 1000, 3000, 1000 for different reinforcing elements which has been given in the first column. For frictional field, right, oxidation reduction potential in volts, frictional field for cohesionless soil, for cohesive materials, maximum microbial activity index 555, maximum organic content in the cohesionless soil for the different reinforcing elements are also given in this table. That means what? We have to also test the chemical constituents of the filling materials. which is see angle of internal friction. We have to also find out under the effective stress conditions. We are talking about the cohesionless soil. So what we shall do? How we can test the angle of internal friction, which is also called as phi. Under the effective stress condition, we can use the triaxial shear test apparatus. We have already discussed that there are three methods for the testing of soil. The UU test and drain test, right? UU test, unconsolidated and drain test, is called a drain test. CD, consolidated drain test, which is called a drain test. And the next one is unconsolidated and drain test, right? So UU test we have studied, CD test we have studied, and consolidated and drain test also we have studied. So using this method, under the effective stress condition, we have to find out the values of phi, and that phi value we have to use. You see, the effective angle of internal friction, whatever the values of C and phi you are going to get, normally for cohesionless soil C will be 0. But whatever the values of phi you are going to find out with the help of triaxial shear test, that we have to know, right? Here what is written there? The effective angle of internal friction of cohesionless soil should be greater than or equal to 25 degree. Whatever the cohesionless soil you are using, that cohesionless soil should have the value of phi greater than or equal to 25 degree. That you have to remember. Otherwise, however, measurement of the internal friction is not required if not more than 15% by weight of field is smaller than 18 micrometer. See, you cannot measure the internal friction. Suppose you have gone for the particle size analysis. In particle size analysis, if the particles, if the particles not more than 15% of the field is smaller than 18 micron, in that case the phi is not required to find out. Then next one is the coefficient of friction between the field and the reinforcing element. How we can find out? The sixth point. See, coefficient of friction between the field and the reinforcing element. In fifth conditions, we have to find out the values of phi under the effective stress condition by the triaxial shear test. Here, what it says that how we can find out the angle of shearing resistance in between the two materials. The two materials means cohesionless soil and the reinforcing element. So what we can do? We can go for the direct shear test also. In case of direct shear test, we can feel the soil, then we can put the reinforcing elements. Again, we shall put the soil, we shall compact it, then reinforcing element, and then we shall go for the shearing. We can find out the coefficient of interfacial friction between soil and the reinforcement using sliding shear box indicates that the coefficient of sliding friction between soil and the reinforcement increases with increase the unit weight of soil and roughness of the reinforcing materials. What is the value of mu? You have to find out here. That is called as the value of the reinforcement. The sliding shear test, what we shall do here, when we are going to do the sliding shear test, two things are there. How we are compacting the soil, cohesionless soil in shear box, right? What is the roughness of the reinforcing element? That is also one of the important. So once you are going for the shearing, in case of direct shear test, we can find out the coefficient of interfacial friction. Interfacial means what is the friction in between the two materials? That is the reinforcing element and the soil. The next test also we can find out, which is called a pull-out test. Pull-out test means we have to pull the materials, right? We have to see nowadays pull-out test already apparatus is there, instrument is there. We can also prepare some models. These tests may be performed in a model or prototype or full-scale reinforced soil wall. Pull-out test. Actually, what we have to do in this case, we have to prepare this sample in such a way so that reinforcing element and soil will be compacted together. And then we shall pull the reinforcing elements. How much load you are applying for pulling and how much displacement is there, you have to plot the graph. You see here, in this test, reinforcing strips are pulled out from the wall and from the wall, and for each strip, a plot is made between the pull-out load and the corresponding displacement. You have to pull the reinforcing element. How much load is going to be taken during the pull-out, and parallelly you have to also note down the displacement. So we can plot the graph, displacement versus load, pull-out load. And from this plot, maximum pull-out load is obtained, right? This pull-out load can be used to calculate the coefficient of operand friction, right? By this formula, F is equal to T by 2 sigma V L into W. So F is the operand soil reinforced friction. T is the maximum pull-out pull-out load, which we have already found out with the help of graph, right? Load versus displacement graph. Sigma V is the normal pressure intensity at the reinforcement strip level, that is gamma Z plus Q. What is gamma? Gamma is the density of soil. Z is the depth of reinforcing strip below soil surface. Soil surface means above the top of the soil. What is the depth of the reinforcing element? That depth we have to consider. And Q is the intensity or the load which has been uniformly distributed over the soil surface. That is the value of Q. L is the length of reinforcing strip we have to take, and W is the width of reinforcing strip we have to consider. So what I am trying to say here, by using the pull-out test, we can also find out the apparent friction in between the soil and reinforcement. This will also help you to know the grip, right? The values of F is more, means more grip is there in between the two materials. Okay, so in that case it can take the more load. So the pull-out test we can carry out. So this is all about the about the cohesionless soil. So geotechnical property of reinforced soil. When we are going to use the cohesionless soil, in that case, whatever the properties we have discussed in these slides, we have to know, right? We have to go for the pull-out test, the sliding shear test, right? We have to also know the angle of shearing resistance based on the effective stress method, right? What is the values of angle of shearing resistance phi? We have to also know about the gradings, that means particle size analysis. We also discuss about what is the facing. Three components are there in the soil reinforcement. One is the reinforcing element, another is the fill materials, which may be the soil or the waste materials also we can use, and third is the facing unit, which is nothing but it is given only for the architectural view, front architectural view of the retaining wall or the embankment, right? So that it look good. It is not going to take the load. So this is all about this today topic. Tomorrow we shall go for the soil reinforcement for the cohesionless soil. Sorry, for cohesive soil. Today we have completed the cohesionless soil. So thank you very much.